In October 2025, the Perseverance rover's night sky cameras recorded a brief but startling flash streaking across the heavens. The motion analysis suggested a speed of around 60 kilometers per second, far faster than any meteor or orbital debris known to exist near the planet. The event's timing appeared to coincide with the predicted flyby of an object cataloged as Interstellar Visitor 3I/Atlas. Within hours, the scheduled data downlinks from several Mars orbiters went dark, and the raw image sequences that would normally appear in public archives were missing. Silence followed, and then came scattered, unconfirmed reports of multiple fast-moving tracks and a faint green flash that for a moment set the scientific community on edge. Early processed frames hinted at behavior no known comet should show, and yet official updates slowed to a crawl. What happened in those missing minutes of data soon became the center of an online storm of curiosity and speculation. Could a fragment of another star system really have passed so close to Mars? And had Perseverance accidentally captured the first clear evidence? 2 days later, an amateur astronomer named Stan Burns, known in online astronomy circles for his careful methodology, released a 9-minute time-lapse compiled from Perseverance's publicly available raw images. The frames were consecutive, time-stamped, and calibrated against background stars. Through them ran a single razor-thin streak. When Burns measured its angular motion, the calculated velocity again reached roughly 60 kilometers per second. That was far above any natural or artificial object typically seen from Mars' surface. For context, NASA's Parker Solar Probe, the fastest human-made spacecraft ever built, only approaches 190 kilometers per second when it dives deep inside the sun's gravity well. Out at Mars' distance, where gravitational pull is weaker, no ordinary comet moves so quickly. If Burns's measurement was correct, the track could belong only to something entering from beyond the solar system. Burns approached the claim with the caution of a professional. He verified each timestamp, cross-checked star positions, and compared the orientation of the rover's masked cameras to eliminate mechanical artifacts. Then he invited the wider community to inspect his data, publishing not just his process video, but also the individual raw frames and calibration scripts. Within hours, tens of thousands of users downloaded the files to test them independently. Some succeeded in reproducing the streak. Others saw nothing but noise. But as replication attempts multiplied, attention shifted to a faint emerald flash that appeared in one group's composite. To some, it looked like an atmospheric emission event, a brief burst of decarbon molecules fluorescing in green light, the hallmark color of cometary chemistry. To others, it was simply a cosmic ray hit amplified by overstacked images. Without access to unprocessed, telemetry-verified data from NASA servers, the debate could not be settled. Burns himself warned against premature conclusions. He emphasized that extraordinary results required extraordinary verification, and that only direct confirmation from Mars orbiters could prove whether the streak was real. But the community's appetite for answers had already grown beyond control. Across online forums, data scientists, astrophotographers, and planetary researchers built competing models of the event. One camp claimed the trajectory matched the predicted motion of 3 Atlas almost exactly. Another insisted the numbers were off by a factor of 2 and dismissed the streak as a statistical illusion. Accusations of faulty calibration and confirmation bias spread through comment threads. The tone of discussion turned adversarial. In one reconstructed animation, a sharp green point appeared near the streak's midpoint at 0.00003 UTC. That single pixel became the spark for weeks of heated debate. Spectroscopists pointed out that green emissions were chemically plausible if sunlight were breaking dicarbon bonds in a comet's coma. Skeptics countered that Perseverance's camera sensors were unfiltered in certain bands and easily fooled by charged particle strikes. Mars' thin atmosphere, they argued, would produce almost no native glow. Without raw, time-locked exposures, the case could not be proven either way. Still, the question refused to fade. Why had the usual trickle of uncalibrated images from the orbiters stopped altogether? Normally, data from headline events appears within days on NASA's and ISA's public servers. This time the silence stretched into weeks. By mid-October, Mars had become the best possible vantage point for observing the interstellar visitor. 3 spacecraft were involved. The Mars Reconnaissance Orbiter carrying HiRISE, ESA's Trace Gas Orbiter equipped with CASIS, and Mars Express with its HRSC camera. Each was assigned a coordinated observation campaign to capture the object during its closest approach, roughly 9 million kilometers from the planet, about 75 times the distance from Earth to the Moon. At that range, even the most powerful lens could resolve only a few dozen km per pixel. HiRISE, optimized for spotting rocks and slopes on Mars' surface, had never attempted to track a fast-moving interplanetary target. Engineers reprogrammed its sequence tables, aiming the narrow field of view ahead of the predicted path using daily updates from JPL's ephemeris data. Each image was a calculated risk. If the targeting was early, the object would fall outside the frame. If late, it would already be gone. CASIS designed for color imaging and mineral studies planned a set of 4-band exposures hoping to capture not just the nucleus, but also any trailing jets or fragments. Mars Express, with its wide swath HRSC, provided the context view, a broad sweep of the sky that could distinguish a compact nucleus from a cluster or plume. The operation required precise timing and coordination between agencies thousands of kilometers apart. No real-time tracking was possible. Every spacecraft would take its snapshots blind, trusting the mathematics of the updated orbit predictions. Even a tiny error of a few arcseconds could mean a total miss. For engineers, it was like photographing a grain of sand while racing past it at cosmic Saint. After the flyby window closed, observers on Earth waited for the usual stream of quick-look images. None came. Not from HiRISE, not from CASIS, not from Mars Express. The delay was explained only in vague terms. Calibration in progress. Data quality review pending. Within JPL, imaging teams reportedly faced an unusually difficult reduction process. For targets moving this quickly, standard correction algorithms designed for fixed landscapes failed. Cosmic ray hits, hot pixels, and registration errors could easily mimic faint fragments. Releasing such frames without exhaustive checks risked global misinterpretation. Each candidate streak had to be inspected manually, compared against predicted motion, and tagged for verification. It was a race between public expectation and scientific caution. Release data too early and misaligned pixels could ignite a wave of misinformation. Wait too long and the delay itself would feed suspicion. Weeks passed as calibration teams moved frame by frame. The outside world saw only silence inside. Engineers reportedly wrestled with questions of precision. Did the predicted ephemeris match the actual track? Were any of the visible features physical, or were they ghosts of noise and cosmic radiation? A comet's characteristic green glow is usually straightforward to interpret. Dicarbon molecules, when exposed to sunlight, emit a bright green light so consistent that comet hunters use it as a diagnostic signature. Yet when preliminary spectral analyses from the Mars campaign surfaced, they told a stranger story. The expected dicarbon emission bands were either weak or absent. Instead, the spectra hinted at an unusual dominance of carbon dioxide gas and a deficit of the simpler carbon chains that create the classic green hue. A green flash without dicarbon was chemically puzzling. If genuine, it implied that another compound, perhaps an exotic metal oxide or an unknown carbon allotrope, was producing the light. Planetary chemists urged restraint, warning that without synchronized calibrated spectra tied precisely to the reported flash, the phenomenon could still be an artifact. The paradox remained unresolved. Then came an even deeper anomaly. The early spectral summary from the Mars Express team indicated strong nickel lines dominating over iron, the reverse of what solar system comets typically display. In ordinary cometary dust, iron emission overwhelms nickel. Nothing in standard models predicted a composition where nickel prevailed by such a wide margin. Meanwhile, Trace Gas Orbiter's instruments detected a volatile mix in which carbon dioxide outgassing exceeded water vapor by almost an order of magnitude. For a body warming under sunlight, that ratio was inverted from expectations. In every model of comet behavior, Water sublimation drives the jets first, with carbon dioxide becoming dominant only at greater distances from the sun. Here, the pattern was flipped. Imaging data, once partially reconstructed, added more contradictions. The primary plume appeared to shoot not away from the sun but toward it. A rare anti-tail configuration sometimes seen in highly dynamic objects, but seldom this sharp. Its brightness gradient was so steep that dust model simulations struggled to reproduce it. To maintain such a concentrated jet without disintegrating, the nucleus would need to be unusually dense and cohesive. Yet, the tracking data showed no measurable non-gravitational acceleration, no subtle pushes or wobbles that normally result from uneven jetting. That behavior implied tremendous mass and inertia, more asteroid-like than comet-like. Each new clue added complexity instead of clarity. As the findings accumulated, the conversation turned from curiosity to deeper unease. Were these simply the signatures of an interstellar object with an unusual chemistry, or did the data point to something beyond natural explanation? The question could not be answered with partial spectra and provisional frames. More data would have to come from later observations if the object remained visible. Then a curious correlation surfaced. A research group comparing long-term orbital integrations noticed that the projected backward path of 3PIB Atlas passed close to the region of sky associated with the famous 1977 WOW signal, the mysterious 72-second radio burst detected at 1420 MHz, the natural emission frequency of hydrogen. Their Monte Carlo simulations estimated roughly a 0.6% chance of such a spatial overlap. Statistically small, yet not impossible. The coincidence reignited speculation. The hydrogen line has long been considered a logical choice for interstellar communication. Narrowband, universal, and energy efficient. No one claimed a connection, but the juxtaposition was intriguing. If any interstellar object warranted a radio follow-up, it would be one whose orbit brushed the coordinates of the most enigmatic signal ever recorded. Skeptical researchers cautioned against reading too much into chance alignments. Positional uncertainty in both the comet's reconstructed orbit and the original WOW signal region was large. Still, the parallel fueled renewed interest in directed radio monitoring. Arrays across Earth prepared to listen when 3PIB Atlas would again emerge from behind the sun. At the end of October 2025, the object slipped into solar conjunction, hidden in glare for 5 weeks. No telescope on Earth or Mars could track it. The gap was expected, a routine observational blackout that accompanies every close pass behind the sun. But this time, anticipation was intense. When the object re-entered view in early December, astronomers planned to scrutinize 4 key metrics: overall brightness, trajectory, plume structure, and spectral fingerprints. If any of them changed, it might indicate fragmentation or a shift in composition. Until then, all anyone could do was wait. The discussion of the Mars event gradually settled into a kind of analytical truce. Supporters of the interstellar hypothesis pointed to the high velocity, the chemical oddities, and the perfect timing with Atlas's approach. Skeptics countered that stacking artifacts, calibration uncertainties, and incomplete spectral calibration were enough to explain every anomaly. Both sides agreed on one thing: only new independently verified data would decide the matter. In scientific terms, separating signal from noise begins with repeatability. Genuine features must appear in multiple datasets, processed independently, and with consistent parameters. Artifacts vanish when the pipeline or calibration changes. The principle is simple but relentless. Extraordinary claims require extraordinary evidence. As of now, the evidence remains divided. Chemically, 3.2/Atlas challenges comet models with its nickel-heavy composition and carbon dioxide dominance. Dynamically, it shows the steadiness of a solid, massive body. Observationally, its fleeting green flash still lacks a definitive source, and statistically, its orbital path's brush with the WOW signal region is little more than a numerical curiosity. Intriguing but unresolved. The data blackout has ended, yet no comprehensive release has appeared. The raw frames and spectra remain in review, awaiting publication. For scientists, that delay is normal. Calibration and verification take time. For the public, it feeds the mystery. What did Perseverance really see that night? Was the streak across the Martian sky a fragment of interstellar ice? A shard of alien metal, or just an illusion created by cosmic noise? And in the silence between confirmed facts and speculation, how much of what we call mystery is simply the shadow of data we have yet to understand? For now, the evidence stands unfinished. A riddle written in pixels and spectra, waiting for the next transmission from Mars to tell the rest of the story.